We are now on our fourth lesson, and this lesson is titled Conservation of Momentum. And our learning objectives for this lesson are that at least at the end of this lesson, you should be able to state the principle of conservation of linear momentum, explain what is meant by the term an isolated system, internal as well as external forces. So those are the things to look out for. Those are the important things that you probably going to be examined on, and then be able to apply the law of conservation of momentum or the principle of conservation of momentum to collusion of two objects. So everything, that's basically what we're really going to be talking about throughout this entire lesson. So what we mean when we talk about the principle of conservation of linear momentum. This is normally, you would normally be asked in an exam to state the principle of conservation of momentum. So you should be able to say what it is. And in simple terms, it says that the total momentum of an isolated system, that's the keyword there, so that system has to be isolated. And you will learn, we'll talk about isolated systems just now, is constant or is conserved. This means that it does not change, it remains the same, hence it is constant. When we do calculation, you'll actually understand what is meant by that. So if it's not making a lot of sense when we perform calculations, it will actually make a bit more sense. So now, one of our learning objectives was that we need to be able to define the term an isolated system. And that isolated system, they say in physics term, that it is a physical configuration of objects that does not exchange any matter with its surroundings or with the environment. So it is not subject to any force whose source is external to the system. So this means that you basically ignore the effects of the environment. Ignore effects of environment. So there is no external force. There is no one applying an external force to that system, and the only forces that we are concerned with is those forces that comes as a component of the system. There's absolutely no external forces, and you will see that we refer as an isolated system. If the system was not isolated, then momentum would not be momentum would not be conserved. So let us now make an example of the difference between an isolated system as well as a non-isolated system. So for an example, let's say we have a very smooth surface, and then we have two balls that are rolling towards each other. Because this is a smooth surface, we would consider this to be an isolated system. There is no external forces acting on these two balls. Isolated system. But then, for example, now let's consider a case where now this is a very rough surface, and then we have those balls. They are still rolling towards each other. But now there's actually, because this surface is rough, they're going to experience a little bit of friction. And that friction is called an external force. This means this system here, it's no longer isolated, and momentum here is not conserved. So for isolated systems, momentum is conserved. So that's the difference. That's how I would at least essentially try to explain the difference between an isolated system and a system that is not isolated, and now understanding what forms those external forces. So friction, for example, in this part, because it's a rough surface, will now affect these two balls, so essentially making that system non-isolated. Okay, let us now then continue our discussion by now differentiating between external forces and internal forces. So external forces, they say the definition of it is that it's a force acting on the pieces of a system that is not caused by a component of the system. For example, we've already spoken about it, and we said, for example, friction, that would be an internal force. An external force, I apologize. And then internal forces would be forces which holds those objects together. Examples of those would be magnetic forces, gravity, etc. So you need to be able to differentiate between these two forces and be able to define what is an external force and what is also an external force. So in an isolated system, where momentum is conserved, we are only interested in internal forces. We do not consider external forces because of Newton's third law. So no, I'm giving it to you as a task to remind yourself what does Newton's third law say, so that you can be able to understand this. And if there was, like I've mentioned before, if there was an external force, we would not have, momentum would not be conserved. Thus, in the absence of an external force acting on the whole system, momentum is conserved. So in an isolated system, we are only interested in internal forces, meaning that momentum is conserved. And for this section, you only need to really worry about isolated system where momentum is conserved. So let us now move our discussion to collusions. So example, imagine you have two balls and they are heading towards each other, and then they go into to strike or collide with each other. In that system, the momentum of the individual, so let's say this is ball one and this is ball two. So the momentum of this ball might change and the momentum of this ball might change, but the total momentum, and you will see we'll perform calculations on this, the total momentum of those of the entire system, because these two balls are what we call, they are a system, and their total momentum will remain the same before and after collusion. So let me reiterate again. So the total momentum of the individual balls, or any object for that matter, can change, but the total momentum of the system remains constant, meaning it is conserved. This means that the total momentum before and after collusion or explosion is equal to the total momentum before collusion is equal to the total momentum after collusion. So this is what you normally used to. Let me just write it down. So here we are. So the total momentum before the collusion, or can be a collusion or an explosion, is equal to the total momentum after the collusion or the explosion. And we can write this in mathematical terms. So we can say, we know that the symbol or the letter for to represent momentum is P. So the total momentum, let's say it's I, the initial momentum, and the final momentum would be F. So the total momentum before collusion and the total momentum after collusion would be the same. So meaning, if we add the momentum before collusion of the individual objects and the momentum after collusion of the individual objects, they should be equal. Then in that way, that momentum would be conserved. So I think if we can explain this equation further by making an example. So imagine that we have two balls in an isolated system where momentum is conserved and they are heading towards each other. There's not enough space there. And then this is before, this is after. So the mass of this ball, we call it M1, and the mass of this one, we call it M2. And this ball is moving with a velocity of V2, and this ball is moving at a velocity of V1. They are moving towards each other. And then they collide, bang. And then after collusion, this ball now moves in the opposite direction, which is M1. And this ball also moves in the opposite direction. So the mass is still the same, M2. Moves now with a new velocity, V1, V2. But this is after the collusion. So if you now remember our our equation. We said the total momentum before collusion and the total momentum after collusion is the same. So this is F for final, I for initial. So we will say we know that, okay, the momentum of ball 1 would be M1 V1. But because it's initial, so it's moving at an initial velocity I, plus the momentum of this one. Remember the formula for momentum, you know what we've discussed, it is the product of mass multiplied by velocity, m2 v2, but it's moving at an initial velocity. Then we say, okay, after collusion, we now have momentum into the momentum of the ball 1, but now it's moving at a final velocity. So that's why we include the F there. Same thing with the other ball, m2 v2 f. I hope that is clear. So normally, so that is that equation. So let us try to perform a calculations, because there are different scenarios that you can play. Sometimes you find that after collusion, only this ball moves and this one maybe remains stationary. Or this ball was stationary and then after collusion, this one moves and everything. So, but now this remains the same. The total momentum before collusion will equal the total momentum after collusion. Sometimes after collusion, these two balls may be joined together and move at the same velocity, and you may be asked to calculate that. But let us then take a quick example. So we have ourselves a very interesting question here, and you can pause the video so that you can jot down the question. It says that a bullet of mass 500 grams is traveling horizontally to the right at a velocity of 500 meters per second and strikes a stationary wooden block of mass 2 kg resting on a smooth horizontal surface. You see that I mentioned the fact that it's smooth horizontal surface. This means that momentum is conserved. So there's no external forces like frictional forces acting on the system. And then they said the bullet goes through the block and comes out the other side now at a speed or at a velocity of 200 meters per second. And our question says that we should calculate the speed of the block after the bullet has come out the other side. So take a minute to jot down the question and then we can start answering it. So the first thing I would do is that I would just draw down a sketch before and after the collusion. So we have ourselves a bullet. So that's a bullet, it looks ugly, and we have a wooden block resting on a horizontal surface. The mass of this is 50 grams. It's traveling at a velocity v1I of 500 meters per second. We need to convert this. So like I said, if you want to convert from grams to kilograms, you divide by 1,000 and this would give us 0.05 kg. So you need to know how to convert that. And then after collusion, now the bullet has actually went through this wooden block and it comes out the other side. So the mass is still the same. The mass, okay, I didn't write the mass of this m2. They said it's 2 kg, and v2, they said it was stationary. So if it's stationary, it means it was not moving. Its velocity was 0 meters per second. Now the mass of this is still the same after the collusion, 2 kg. Velocity, that is what we are asked to calculate, v2f, v2i. So we don't know what that is. And then the velocity of this v1f is now 200 meters per second, and then the mass is still 0.05 kg. Okay, that is fine. So we have listed all our quantities that are there, and we've drawn the sketch. And now let us say, okay, let's take to the right as positive and then to the left as negative. So we now have to write down that equation of ours of the total momentum before collusion and after collusion is the same. So we have P, T, where am I taking T? So the total momentum before, total momentum after collision is the same. So now we have m1 v1i plus m2 v2i, which is equals to m1 v1f plus m2 v2f. So then it's just a matter of what do you call substituting now. So we have 0.05. Initial momentum is to the right, it's positive, so it's going to be 500 meters per second, plus the mass of this is 2 kg. They said that it is stationary, so this is 0. M1 here it's 2, we don't know v1f, that's what we're looking for, the velocity of this wooden block after collusion. And then m2 here, it's still 0.05 multiplied by 200 meters per second, it's still to the right, so it is positive. And then if you put this in your calculator, you'd find that 0.05 multiplied by 500, that is going to give us 25. 2 multiplied by 0, you know that is 0. 2 multiplied by 2, let me remove this. So we have 25 plus 0, which is equals to 2v1f plus 0.05 multiplied by 200, that is supposed to give us 10. And then if you take the 10 to the other side, it's just 25 minus 10. That is how much is that? This is going to give us 15 is equals to 2v1. So this is maths, that's why I'm not ready to divide both sides by 2. And then essentially you come to an answer that 15 divided by 2 is how much? 7.5. This cancels these 2, then you have v1f. I'm sorry that was not in the picture. So yeah, we took the 10 to the other side, and then 25, this 10 became negative, so we have 25 minus 10, and then we're left with 15 on the side, which was equals to 2v1f. So we want to be left with 2 v1f on the other side, because that is what we're solving for, which is the velocity of the wooden block after collusion. And then that means we divide both sides by 2, so 15 divided by 2 is going to give us 7.5. So we found our answer to be for v1f to be 7.5 meters per second. It's positive, and we had agreed that right is positive, and then our left would be negative. What does this mean? This means that the velocity, therefore the velocity of the wooden block after collusion is 7.5 meters per second to the right. So we have definitely calculated that, or you can say maybe in the same direction as the bullet. And yeah, this I think brings us to the end of this lesson. If you have questions, remember you can always send me a WhatsApp. We can talk in the WhatsApp group.